Very well. Let's take a look about something known as ice tables, which is technically the heavy-duty math portion of this lecture, right? We've done a little bit of derivations in the previous videos, but here's where we're actually going to do the heavy-duty math involved with equilibrium problems. And we use something known as the ice table. I stands for initial concentration, change in concentration, and equilibrium concentration. So you basically create a little table that tells you how the concentrations of reactants and products are going to change from their initial values all the way to the equilibrium value. Because ultimately, what's happening when you mix two reactants together is that they do react to give you products to some extent. The extent of that reaction is determined by the value of the equilibrium constant. And until the equilibrium is achieved, you are going to observe a change in the concentration for your reactants and for your products. So your reactions are trying to achieve equilibrium every single time. All right, so this is the idea. For this particular problem, we're actually looking for the value of the equilibrium constant based on the idea that the initial concentration of H2 is 1 times 10 to the negative 3 molar. The initial concentration of I2 is 2 times 10 to the negative 3. And the equilibrium concentration of HI is 1.87 times 10 to the negative 3. So paying attention to those subscripts is going to be important. All right, so the ice table, which by the way, they actually are places where you find tables made out of ice. Completely unrelated to this, but I thought it was kind of cool to share that with you. This one in particular is present at some bars in Vegas, or so I heard. You can go into these bars that have basically very cold. They keep it cold so that you won't melt the ice. But the bar, the tables, everything is made out of ice, which is kind of an interesting contrast. Considering that Vegas is usually pretty hot in general. All right, so here's your ice table. Technically, what we do is we arrange columns based on the reactants that you have present and the products that you have present. So you have H2, I2, HI, so those are your columns. And the rows are simply the ice parameters, right? The initial concentration, the change in concentration, and the equilibrium concentration. So for initial concentrations, we know that the value for H2 is 1 times 10 to the negative 3. The value for I2 is 2 times 10 to the negative 3. But in the problem, I said nothing about the initial concentration of HI. This is going to be a common theme for all the equilibrium problems that we're going to encounter in this class. So whenever you don't have information for one of the products or reactants, it is assumed that the initial concentration is 0. So we're going to input just 0 for HI as far as the initial concentration goes. Now the change in concentration typically is given in values of x, because you don't know to what extent this reaction is going to happen. So here's where the balancing coefficients take central role in the process. You look at H2 and I2, they both have a coefficient of 1. On the other hand, HI has a coefficient of 2. So whatever extent of reaction takes place is going to be based on those coefficients. You will have the reactants decrease in concentration as you move forward to the product side by a value of 1 based on the balancing coefficients, but you will form HI, you will increase its amount by a value of 2 based on the balancing coefficients. And since we don't know the extent of that coefficient, we're simply going to use x's to symbolize that extent. But you have to keep the proportions correct, right? So if the balancing coefficient is 1 for H2 and I2, then you're going to subtract x, 1 times x from each one of them. On the other hand, for HI that has a coefficient of 2, you're going to have to add 2x because, the amount by which HI is being formed is twice as much as the amount of H2 or I2 getting lost. All right, now the equilibrium concentration row is pretty much nothing more than the addition of the initial and changing concentration rows. So here you have 1 times 10 to the negative 3 minus x, 2 times 10 to the negative 3 minus x, and 0 plus 2x, which is just 2x, right? So these are the equilibrium concentrations based on the table. So here's where the information I gave you at the beginning gets to be utilized, at least for HI, right? I told you that the equilibrium concentration of HI is 1.87 times 10 to the negative 3. So that means that the 2x that we have here for HI as equilibrium concentration, that 2x has to equal 1.87 times 10 to the negative 3. So if we solve for x, right, divide this by 2, now we know that the equilibrium concentration of H2 and I2 is going to have to be the 10 to the negative 3 minus 9.35 times 10 to the negative 4, or the 2 times 10 to the negative 3 minus 9.35 times 10 to the negative 4. So now we know that those are the values of x. So when you input that into the equation, you find out that the equilibrium concentration is going to be 6.5 times 10 to the negative 5 for H2, 1.065 times 10 to the negative 3 for I2, and of course 1.87 times 10 to the negative 3 for HI. Now that we know the equilibrium concentrations, okay, I'm going to make some room here, we can finally input the products over reactants as an expression for your equilibrium. And once again, because HI has a balancing coefficient of 2, you're going to have to raise the HI concentration to the power of 2. Divided by the concentration of H2 to the power of 1 times the concentration of I2 to the power of 1. So we simply input the concentration values that we just found out, and we raise into the corresponding coefficients. And if you do this correctly in your calculator, which by the way, since we're going to be dealing with exponential numbers, I highly advise that when you divide numbers from each other, that you use parentheses for those numbers that have exponents. Your calculator sometimes will misinterpret that if you don't have the parentheses. Okay, but the value of the Kc now is found experimentally as being 51. And simply stated, the procedure that we have enacted in this video is literally the procedures that you utilize experimentally to find the equilibrium constants. You have to measure the concentrations of all the species. So usually you use some type of spectroscopy to figure out the concentrations in a very similar manner that we utilize them to find the kinetics concentrations for reactions, right? But this time we're looking for equilibrium concentrations. So it's one of the ways in which you can do this. Not the only way. There's other means to derive the equilibrium concentration, as you'll find out in future lectures. But the idea is that when you're dealing with equilibrium expression, you have to have the equilibrium concentrations in here. All right. So let me show you a few ways in which you can solve I-stable problems where you actually have the value of the equilibrium constant given from the get-go, and instead of trying to find the equilibrium constant, what you try to find out is the equilibrium concentrations. There's different ways to approach this. The sure way to get it is by using the quadratic formula. And in this video, or excuse me, in this slide, I'm showing you the derivation of the quadratic formula, right? You don't need to know the derivation, but it's kind of a nice little, rundown of how you get to negative b plus or minus square root of b squared minus 4ac all divided by 2a. I'll show you during the discussion sections that there's a different way to utilize the quadratic formula without having to use so many expressions. We'll talk about that on a different video. But for now, in this lecture, I'm going to stick to the traditional quadratic formula. Negative b plus or minus square root of b squared minus 4ac all divided by 2a. Alright. The way we're going to use the quadratic formula ultimately has to do with the fact that we're going to end up with some expressions, some polynomial expressions that will be raised to the power of 2. So check this out. We have a simple equation here, N2O4 turning into two NO2s. And we're being told that the initial concentration of N2O4 is 1.50 molar, and that the equilibrium constant of the reaction is 4.61 times 10 to the negative 3 at some temperature. The key question being, what are the equilibrium concentrations of the reactants and products? So here we don't know the equilibrium concentrations, but we do know the equilibrium constant. So what we have to do first is set up an equilibrium I-stable. Alright, so we have the reactant, we have the product, and we have the ice rows, right? Initial concentration, we've been told it's 1.50 for N2O4. We have been told nothing about NO2, so that means that the initial concentration can be regarded as being 0. The change in concentration is based on the balancing coefficients. A coefficient of 1 for N2O4, a coefficient of 2 for NO2. So you will decrease the reactant concentration by minus x, but you will increase the concentration of NO2 by 2x, right? So pay attention to those balancing coefficients. It's important that you don't forget to look at them so that you don't mess up this, part of the equation. And adding the two rows together will tell you that the equilibrium concentration of N2O4 is 1.5 minus x, and the equilibrium concentration of NO2 will be 2x. All right, now let me make some room, because now we have to use those equilibrium concentrations to set up the equilibrium expression. And the equilibrium expression in this reaction is NO2 raised to the power of 2 divided by the concentration of N2O4 raised to the power of 1. Since we know the concentration of NO2 to be 2x, we're going to be raising 2x to the second power. And since we know the equilibrium concentration of N2O4 to be 1.5 minus x, that's what we're going to have in the denominator raised to the first power. All of that equates to the equilibrium constant 4.61 times 10 to the negative 3. So what we do to solve this problem is cross multiply both sides by 1.5 minus x. And also I went ahead and distributed the square, right? Distributed the square to the 2, distributed the square to x, so you have 4x squared on top. Now if you cross multiply both sides by 1.5 minus x, you're going to end up with the following expression. You're going to have a new number minus another number multiplied by x that equals 4x squared. If you bring everything to the right side, so if you add 4.61 times 10 to negative 3x from both sides and subtract 6.92 times 10 to negative 3, you'll end up with the following polynomial expression, which equals 0. This is the expression that you want to have before you set up your quadratic formula. Simply stated, the coefficient in front of x squared is your a, the coefficient in front of your x is your b, and the coefficient without the x's is your c. And you gotta be mindful of the sign. The sign is part of the value of c, or the value of b, or the value of a. Alright, so here's where we get to use the quadratic formula. And I'm gonna make a little bit more room here because we need to do a few steps. Okay, so a is 4, b is positive 4.61 times 10 to negative 3, and c is negative 6.92 times 10 to negative 3. So I'm gonna input those values, which I'm showing the equation right here, into the quadratic formula. B is 4.61 times 10 to negative 3, so negative b is going to be negative 4.61 times 10 to negative 3, plus or minus the square root of 4.61 times 10 to negative 3 squared, minus 4 times a is 4, times c, which is negative 6.92 times 10 to negative 3. All of this gets divided by 2a, and a being 4 means that you will multiply 2 by 4. So what I recommend that you do in this process is go ahead and try to simplify. And notice that from this step to the second step, I disregarded the negative because the value of x that you get has to be a number that's positive. And not only that, a value that's positive but small enough that you're not going to end up with subtractions that lead to negative values. Okay, so in this case, the negative option is really not going to work out for us. But what you need to do is multiply 4 by 4 by 6.92 times 10 to negative 3. You're going to get a number in your calculator. To that number, you're going to, in this case, add 4.61 times 10 to negative 3 squared, and you're going to get the following number, 0.110741, inside the square root. So here, what you do is you take the square root of that number, which will yield the following expression, 0.332778, which is being added to the negative 4.61 times 10 to negative 3, all divided by 2 times 4, which is 8. So upon adding the two numbers on top, or technically subtracting them, you're going to end up with a positive number, which upon division with 8 will give you 0.0410. This right here is the value of x. So all you need to do is input this value back into the expression, right? So you have 1.5 minus 0.041, and you have 2 times 0.041 to find out the actual equilibrium concentrations of N2O4 and NO2. Alright, so this is the long way of approaching these problems. You have to use the quadratic formula for some of them, but I'm going to show you in the next video how you can use certain approximations to simplify the process. And some equations you won't be able to use the approximation, in which case you're stuck with the quadratic formula. In other ones, you'll be able to, and I'm going to show you in the next video how to recognize when you can use the approximations.